All right, z-scores, sorry, can't help it. So I'm just gonna go over the key that I have here um, to help you out. So in the US, the average IQ is 100, standard deviation is 15. So I went ahead and filled out a normal curve just to illustrate the point and to make it easier perhaps for you to grasp and understand, right? So 0.15 here percent and the associated z-scores with those values. Of course, we know this is continuous. There are values anywhere in between, but these are the ones we know for sure when we make our normal distribution. Okay? And so what percentage of the population would you expect to have an IQ lower than 85? So lower than 85. Um, yes, you could use your curve, but use your calculator if unless I tell you to use the graph, right? So I'm just going to use negative, what is this, 1 million here. So you use normal CDF because you want to know the percentage or the probability of someone having an IQ less than or lower than 85, right? So that means that you always want to read it from left to right. So you're saying, hey, I want to go as far as I can possibly to the left, all the way up to 85, right? So as far to the left, all the way up to 85. Average standard deviation, I multiply that by 100, I get 15.86. Very similar to what you did when you just added the values from the graph, right? Next, what percentage of the population would you expect to have an IQ between 90 and 120? Right, so between 90, which is somewhere here, and 120, we want to know that. In this case, right, both values are provided, the lower limit on the left and the upper. Mean standard deviation, you multiply it by 100, you get 65.63%. The next question says, what IQ? So they actually want a value, right? And they're giving you the percentage. That is indicating to you that you're going to have to use inverse norm because normal CDF finds the percentage under the curve between values or below a certain value, above a certain value. Inverse norm actually gives you that value along the x-axis that you're interested in. So what IQ would one have, sorry, if only 40% of the population scored higher on the test? So 40% scored higher. Remember, in the middle it would say 50 or 50 on either side. If it says 40 or higher, you automatically assume that you're higher up the curve because there's 40 on this side, therefore more of the curve is to the left. And in fact, we want the 60 in inverse norm, 0.6, mean standard deviation. So an IQ score of 103.8 would make that happen, okay? So that's how that works. What if they asked for the z-score, right? Uh, what would the z-score be of so that 40% is above 60 or below? Because remember, every score or every value along the x-axis also has a z-score. Well, you have choices. You can use the formula, right? And I don't want to write on here because if I just post a PDF and some folks might not look at the video and they might confuse them, why is that there? But you would simply go inverse norm 0.6, 0, and 1, because when it's the z-score, you're knowing that the average is 0 and the standard deviation is 1. But you could also use the formula for z-score that I gave you. Either one of them would work in this case. Next, suppose that you're told that the heights of adult males in a particular region of the world is normally distributed with 70 inches as your mean and a standard deviation of 2. What proportion? Same, probability, proportion, right? Percentage would be between 72 and 73 inches. Okay, we are given both the low and the upper, mean and standard deviation, so we know that's 9.18%. It's asking for percentage, so it's normal CDF. What height corresponds to the point where 20% of all males are greater than this height. Okay, not so you got to watch out for that, but usually when it gives you an indication that the percentage given is above the value you're after, in this case height, right? You should have that notion that you're higher up the curve to the right, because the further up you go, the taller, right? And so that only 20% would be taller than this value, which means that 80% would be shorter than that value. And that's the number you want into inverse norm. Always the percentage of males in this case that would be below that height. Okay, that's how it works. We always read our graph from left to right. In any unit we do always left to right. And so that's the height that would make that happen. So if you were 71.68 inches tall in this case, you would be considered, right? You would have 20% above you or taller than you, and 80% of males would be shorter. What height corresponds to the point where 20% of all adult males are less than this height? 20% are less than this height or are shorter than this height. In this case, they're actually giving you, right? It couldn't be up here, because if you said it's somewhere up here and 20% are shorter than you, it's not right, because 50 is down the middle. So it has to be to the left of the average somewhere where you make that line. This is not drawn to scale, right? But in this case, it's 0.2. So no need to subtract from 100% to get the left. Left is already given. And so that is your height for that particular case. The backside, let me pause there for a bit. I'm going to first check there to see if I can explain it better. Here is the weight of a chocolate bar, right, has a mean of 8 and a standard deviation of 0.1. What is the weight of the chocolate bar with a z-score of negative 2.7? In this case, they want the actual value, right? It's like, hey, what would that weight be along like at the bottom of the curve, if you imagine, right? And knowing that 0's in the middle, if you go 1, 2, 3, it's somewhere here, right? We want that weight here with a z-score of negative 2.7. This would be negative 3, negative 2, negative 1. And remember that every z-score has also a weight associated with it, because we know that in the middle you would have a weight of 8 ounces, and then this would go down by 0.1 every time you go to the left, and up by 0.1, right? If we actually graph the weights that correspond to the z-scores. I would just use this formula. X is equal to, this formula is in your notes, right? So you would have Z times standard deviation plus the mean. Okay. And so we just take the z-score, which is negative 2.7, times the standard deviation, which is, 0.1, plus the average, which is 8. Okay. And so you just go ahead and compute that, and you get your answer. So this would be negative 0.27 plus 8. That's 7.73 ounces. That's all you have to do there. There are other ways of using a combination of inverse norm and normal CDF. If you figure it out, great, good for you. I will just leave it at this, okay? And for B, chocolate bars less than 7.75 ounces are rejected and not sold in stores. If the factory produces 12,000 a day, how many are usable, right? So first we need to figure out the percentage, right, of bars that would be rejected. So percentage rejected, or let's do it that way, would be normal CDF. So anything less than 7.75 is rejected, meaning, right, we need to have a very low number for our low limit all the way up to 7.75. And then we just have our mean and our standard deviation followed. So you figure that out. Let me just see here. If you plug that in, so these are rejects, right? So we want to know usable. So I have to read very carefully, right? So rejected bars would be 12,000 times whatever you get from this. Okay, so we're going to figure that out. Normal CF. Oops. Okay, you enter all that information and you get 0.06 0062, 4 decimals there. So if you multiply what you have in your calculator times 12,000, that's 74 or approximately 75 bars, right? So I'm going to write down 74.51, keeps going, which is approximately 75 bars that will be rejected. Therefore, usable would be 12,000 minus the 75, right? That is 11,925 bars will be usable. So there would have been a different way of doing this as well if you figured out 7.75, right, and above. So this would have been plus 10,000. That would have been the percentage of usable bars already. So if you multiplied 12,000 by that, then it would have saved you from having to subtract by 75. All right. Next, 2006, the age of mothers who had children aged 4 and under were approximately normally distributed. Determine the percent of mothers who are under the age of 18. Lots going on here, but the first thing you would want to do is find your mean and standard deviation based on this. The mean age of mothers and that would have children age 4 and under. Okay, so the midpoints, right? 15 plus 19 divided by 2, that's 17. 20 plus 24 divided by 2 is 22. And so you will find that you go up by 5. It's 47 here. Okay, so that's your midpoints. That'll be L1. This would be L2. So I would add, like on a test or a quiz, I would probably ask you to find the mean and standard deviation, right? So the mean is, I'm just going to give you that number, 31.99 years, and the standard deviation is 5.82 years. Okay. Maybe I will write down, I went one variable stats, L1, L2. Okay. That's for A. And then now we can answer B, right? Determine the percent of mothers who were under 18, right? So you would say normal CDF. We go negative 10,000 all the way to 18. Average age of 31.99 with a standard deviation of 5.82. Right? And so what do we get? We get, times 100, sorry. We get 0.81% of mothers. Okay. So yeah, a lot of pieces going on here. Normally it would have been probably more guided like that. So for the bonus, I will say this. It says in a population, 50% of adults are taller than 180 and 10% are taller than 200 centimeters. Okay? Determine the mean and standard deviation of for this population. Okay, basically, there are probably more than one way of doing this. But if you consider a normal curve and down the middle, because we know 50% of adults are taller than 180 centimeters, that also tells us that 50% are shorter than 180 centimeters, because we know it's normally distributed. So we in fact are given the mean, which has a z-score of 0, okay? Because we know that this is 50%, okay? Or shorter at the same time. Okay, 50% are taller, meaning 50% are shorter. If it said 40% are taller, that would have meant 60% are shorter. So if you give me above, I know the percentage below and vice versa, right? So anyways, we know the average because of the 50, right? So that is a given already. I will just state that. That is known to us. The other part is the standard deviation is a bit more challenging. We know that 10% are taller than 200 centimeters. That means that you're somewhere up here, right, where 10% is taller. And we know that the this height is 200 centimeters. Okay, I don't know what the z-score is, but there's a way to figure that out. Because if this is 10%, then I know that this all the way here is 90. Okay, I don't want to write over this part, but if this is 10, then this is 90. So basically the z-score for 200 centimeters, for a height of 200 centimeters, would be this. Inverse norm of 90%, 0.9, would have an average of 0 and a standard deviation of 1. Here I'm going to get this is going to give me the z-score for a height of 200 centimeters. Okay. And you're like, can't I use the formula for z-score? Well, you don't know the standard deviation, so that's the problem. And so we're going to go and call that inverse norm 0.9, 0, and 1. So that z-score is 1.28. Okay. So we now know that this has a z-score of 1.28. And when you have both values and both z-scores, you can use this formula, right? I said upper value minus lower, and then you go z up minus z low. Okay, so let's do that. Upper is 200 minus lower is 180, and then the z-score for the upper is 1.28, and the z-score for the lower is 0, right? So you end up with 20 over 1.28. And we're going to do that, divide it. That's 15.625 centimeters. That is our standard deviation, 15.63 or 625, you name it. That's what that is. Okay. So this is a bonus, of course, but you should be able to apply that. Okay. All right. Take care.